Commonly used to reactions involving iodine are commonly used to investigate rates of reaction. One reaction involves hydrogen and iodine reacting together to form hydrogen iodide. A little equation of that, so we've got H2 plus I2 goes to 2HI. This reaction is thought to occur by initially breaking bonds in one of the reactants. Explain using bond enthalpy which bond is most likely to break first. Okay, so you go to your data book and you find that the hydrogen to hydrogen bond enthalpy is 436 kilojoules per mole. That's how much you need to break 1 mole of those. The iodine to iodine bond enthalpy is 151 kilojoules per mole. Now, if you've gone and got that, then it should be pretty clear that iodine is going to break first. Okay, you just need to recognise that we have a lower energy requirement to break the iodine for iodine to iodine, so it will break first. That's your mark. Okay. The graph shows the distribution of kinetic energies of reactant molecules in the gas mixture at 300 degrees C. Add a second curve to show the distribution of kinetic energies at 400. Okay, so I need to put in a curve that is basically higher up than this, or sorry, not higher, because it's not necessarily higher, but further to the right. Okay, so I'm just going to shift a curve and that'll get the mark. Anything which has further up, and we expect a slightly lower bump, they tend to spread out more, but as long as it's not higher, then it's good. That's it. The reaction to produce hydrogen iodide is exothermic. State the effect of increasing temperature on the position of equilibrium. Okay, so if what they're saying is that the forward is a negative delta H. That's the exothermic. If I increase temperature, I am not going to favour the exothermic because Le Chatelier says whatever you do, it will try and minimise that disruption. So I've heated it up. So it's not going to actually favour the forward, it's going to favour the back. So what we're going to do is we are going to, because it says what the position is, we're going to shift it to the left-hand side. Or two products. Sorry, two reactants. State why changing the pressure has no effect. Okay, so pressure is about gases. On the left-hand side, I have 2 moles of gas. On the right-hand side, I have 2 moles of gas. That means that even if I shift the pressure, there is no way for this equilibrium to do anything about the fact I've shifted the pressure. So if I squeeze it, normally you'd say is okay, it would shift to the side with less moles of gas. There is no side with less moles of gas. So basically, that's it. There's no difference in moles of gas on each side. Potential energy diagram for the reaction between hydrogen and iodine is shown. State the term for the unstable arrangement of atoms. This is the one that's shown up here. Just got it straight up, know that. That's the activated complex. Calculate the enthalpy change in kilojoules for the forward reaction. Okay, so what we've got is the EA for the forward going up here, from here to here, and the EA for the back going from here to here. So what we've got is, that's my delta H. So I just need to take this away from this. And I know it's a negative, okay? So it's a pretty straightforward calculation for this one. 182.8 minus 173.2 gives me 9.6. That's a minus kilojoules per mole. Platinum can be used as a catalyst. State the effect that platinum would have on the activation energy. So remember, catalysts do this. They drop the activation energy, and that's it. So lower, decrease, whatever you prefer to say for it. Okay. Sorry, that was not the question. So there might have been a little kind of scribble in the middle of that one. Okay, the reaction between iodide ions and persulfate ions is used to investigate the effect of changing concentration on rate of reaction. Relative rate of reaction is determined by mixing the reactants in a beaker, recording the time taken for it to change colour. Results of the investigation are shown. We've got a nice, pretty straightforward table. The instructions state that a dry beaker must be used for each experiment, suggests a reason why the beaker should be dry. Okay, well, we're looking at concentration. So if we had water in the beaker, then whatever you put in is going to change the concentration. So basically that's it. It would affect or would change concentration. Okay, calculate the time in seconds for the reaction in experiment 3. Okay, so we're looking for time here. What we've been given is the rate. So rate 1 over t from databook. So t is 1 over rate. It's it's s to the minus 1, so we're going to get our time is going to be in seconds. So t is 1 over 0.00819, and that will give you 122.1 seconds. And that's it. Explain why decreasing the concentration of iodine ions lowers the reaction rate. To be honest, this is a very, very simple question. Just not nice. Just you have to remember what you're talking about here. We're talking about collisions. And what we're saying is collisions less likely. Or you just have less collisions. So lower rate. And that's it. And this is definitely the end of this question.